Right.
Hey, sorry about that.
That's all right. I had the wrong phone number, I guess. So I'll put that in permanently as the number to text it to. So what are we going to do tonight?
Right now I'm on kind of solving logarithmic equations.
Okay, cool. Those probably you probably verbalize those to me. So
yeah. So I'll just start with one. So it's the log of 2x equals -1.
the log of
2 base x.
the log base 2 of x equals -1.
Mm-hmm.
Like that. Okay.
Yeah.
What is the exponential expression of that? That's the logarithmic equation. What would the exponential equation be?
I'm not too sure.
Okay, to convert back and forth, let's just review. Y equals b to the x means that the log of y base b equals x. So these two are equivalent. And the way to really solve the log expression is to express it exponentially. And the way I remember how to do it is I take the number on the far left, I raise it to the power of the number on the far right, and it's equal to the argument. So I have 2 to the -1 equals x. What's 2 to the -1?
Well, I should know this, but I don't.
It's 1 over 2 to the 1. Whenever you have a negative exponent, in other words, 3 to the -4 equals 1 over 3 to the 4. It's as straightforward as that. Notice it has nothing to do with negative numbers when you have negative exponents. It merely means the reciprocal.
Yep.
Okay, so in this case, 1/2 equals x. And as all I had to do was convert it to its exponential expression.
Yeah.
Okay. All right, what else you got?
Let's see, what's log base 5, and then 2, parentheses 2x plus 15 equals log base 5 to 3x.
Equals log base 5 of what?
To the 3x.
3x?
Mm-hmm.
Okay. When you have the log of an argument equals the same base log of a different argument, then you can equate the arguments. It's kind of like saying if I have 3 to the x equals 3 to the y, then x equals y.
Yeah.
Similar here. So is all I really need to say is 2x plus 15 equals 3x. Solve that?
So x.
I'm sorry?
X equals.
Yeah. In other words, we move the 2x over to there, and we leave the 15 there, and like that.
Yep.
Okay?
Alright. And then, let's try this one. Alright, natural log x plus the natural log of x minus 2 equals 1.
Having a little bit of a difficulty hearing you. Did I get that right?
Yep.
Okay. There are 3 extremely important rules about logs. One of them, and it doesn't matter whether it's natural log or regular log. If I take the log of the product of 2 things, it's equal to the sum of the logs. Okay. If I take the log of the quotient of two things, it's the same as the difference of the logs. And if I take the log of a number and raise it to a power like that, it's the same as that power times the log. So let's number these rules, because these rules are huge and doing most anything with logs. So what I have here is the sum of two logs. So you want to be able to go backwards and forwards between these two rules. When you go to the right, you're expanding. When you go to the left, you are compressing.
Yep.
In this particular case, we want to compress. It's already expanded. Okay? So what can I say here based on rule number 1?
Would be the natural log of x times x minus b equals 1.
Yeah. Now, that's the same as the natural log of x squared minus 2x equals 1, right? Did I get that right?
Mm-hmm.
Yeah. And now to solve this, you got to put it in exponential format. So you need to do this translating back and forth between logarithmic format and exponential format a lot. What is the base of the natural log? In other words, what is this number right here if I were to write it?
Would it be 10 or is that only for logs?
It's e. That's the number e. That's what natural log is. In other words, log base e equals natural log. Okay. So now put this in exponential expression.
Then would be x squared minus 2x minus 1 equals 0.
No, we're going to take the number on the far left. Remember, e is just a number. We're going to raise it to the power of the number on the far right, and it's equal to the argument. So I have x squared minus 2x equals e to the 1. That becomes a quadratic that you can solve using the quadratic formula. This is a little bit of a strange problem, actually. You sure the whole thing was equal to 1 and not 0 from the beginning? It was all equal to 1?
Yep.
Okay. That's fine. It works. It's just I can't say that I've seen this kind of an equation before. A quadratic that had e as your constant. But this one does.
Never seen that before.
Now, there's another way to look at this when I have it like this. And that is, you can, how do I describe this? This is always tough to describe. Let's say I have x equal y is an equation. Well, I can take e to the x power and let it equal e to the y power. In other words, the left side is now e to the x, the right side is now e to the y. This is a process that we don't do very often, but it's useful sometimes when one side is natural log. In other words, I'm going to exponentiate both sides of this equation, and when you take e and raise it to the natural log of something, it's equal to the something. So now I get directly x squared minus 2x equals e, which is what I got when I merely translated that back into exponential expression.
I think I'm picking this up for the most part.
I'm sorry, what?
I think I'm picking this up.
Okay, good. It's really a question of these three rules. These three rules are huge. Right there. Let me leave them on for a moment, although you want to get to a point where you have them memorized so you don't have to look them up each time. One way that I memorize these is you always do one level less mathematically. In other words, if I'm doing multiplication in the argument, then I'm going to do addition. If I'm doing division, I'm going to do subtraction, and if I'm doing exponentiation, I'm going to do multiplication. So I always do, you can think of addition as being one level less than multiplication. And when you think of it like that, it works for all three of these rules. One thing you got to be a little careful with those rules. If you look at them, when you get a problem like this, what does that equal to? It's a trick question. It's really equal to the log of a plus b. In other words, that does not do anything. We have addition taking place in the argument. Well, none of these rules handle that. If you have addition of two logs, then you can combine them into the log of a times b. But if you have the log of two things that are being added together, that doesn't simplify. So just be aware of that it can be a little confusing. So what's the next one you have?
Next one is 1/2 log base 6, and then 16x equals 3.
Equals 3?
Yep.
Okay. What can I do with this 1/2?
Wouldn't you just multiply everything by 2?
What's that?
Wouldn't you multiply everything by 2?
Yeah. There's actually a couple things you could do. That's the smartest thing to do, probably. But notice you could also make it the exponent of that log. In other words, by using Rule 3 in reverse, that 1/2 was in front of the log. So I can take that coefficient and make it the exponent of the argument. But it's actually a little bit better to do it your way. Multiply both sides by 2, and you have the log 6 of 16x equals 6. Now what can you say?
Wouldn't it be 6 to the 3rd power equals 16x?
6 to the 6th power equals 16x.
Oh, sorry. I forgot that you have to multiply both sides by 2.
Well, oh, okay. Yeah, in this step here, right. To get rid of that 1/2, yeah. And then this, of course, you do on a calculator. So x equals 6 to the 6th power divided by 16.
Sweet.
Okay.
15 plus 2 log base 2 equals 31.
Of what, x?
Of just x equals 31.
Did I get that right? Okay.
Mm-hmm.
So what's my first step?
You want to subtract 15 from both sides.
And my next step?
Divide each side by 2.
And my last step?
You want to have 2 to the 8th power equals x.
Correct. And I think 2 to the 8th power, I believe, is 256.
256?
I think so. 2 to the 10th is about 1,000. So 2 to the 8th would be about, it goes 64, 128, 256, 512, 1,024. So I'm pretty sure 2 to the 8th is 256.
Alright.
Okay.
Then let's go with the next one. Natural log of x plus 5 equals the natural log of x minus 1 minus the natural log of x plus 1.
Okay? Now,
So first,
you can't divide both sides by natural log. Okay? That's not, if you have the natural log of one thing equals the natural log of something else, then you can equate both arguments. But here we have two natural logs over there. So what can we do on the right side?
wouldn't you want to compress it?
Yes. So it would be
X minus 1 divided by x plus 1.
That equals natural log of x plus 5. Now, you essentially can divide by natural log, although that's not what you're doing. It's important to know that this is not that multiplied by that. This is more of like f of x.
Yeah.
Okay? So, however, if you have the natural log of an argument equals the natural log of a different argument, then you definitely can set them equal to one another. How do I solve that?
And then I guess you'd multiply each side. Multiply each side by x plus 4.
By x plus 1?
Oh, that's 1. Yeah, x plus 1.
Yeah. So on the left side, I get x squared plus 6x plus 5 equal x minus 1. What next?
And then you subtract x and add 1.
And
then maybe x plus 2 and then x plus 3.
okay. So your solution. Now, with logarithms, when you come up with two solutions, almost always one of them is extraneous. One of them is going to violate the domain. Now, in order to check, we have to go all the way back to the original equation. You cannot check domain violation from step 2. Even though I've told you that step 2 is exactly the same as step 1, it isn't in terms of domain. Now, minus 2 and minus 3. Well, we don't violate that domain. We do violate that domain, and we violate that domain. What does that mean? There is no solution to this problem that you gave me. This is a very unusual one where you have no solution. And notice also, well first of all, you understand about the domain of natural log functions?
I do not.
Has to be greater than 0. Can't even be equal to 0. You cannot take the natural log of 0. You definitely can't take the log of any negative number, in the same way that you can't take the square root of a negative number. When you have the square root of x, the domain of that is x has to be 0 or positive. Well, when you have the natural log of x, or log of x, x has to be greater than 0. It can't even be equal to 0. And both solutions we came up with would cause us to be taking the natural log of a negative number. Even this one, when I substitute minus 2 and minus 3, I get the natural log of a negative number. Now, notice that if we plug it into that, we don't violate the domain, because you end up with the natural log of minus 3 over the natural log of minus 2. Well, that ends up being a positive number now. Negative divided by negative is positive. So it's entirely possible that when you use one of the log rules, like we did here, to compress that, that it produces an argument that does not violate, whose domain is not violated. But that's why it's extremely important to go to the original problem to see whether you have domain violation, and we do here with both answers. So this has no solution.
All right.
Usually just one of them violates it. And when one of them violates it, you toss it out. But when both of them violate it, you can't have x equal to -3 or -2.
So you have to go back to the original equation.
Yes.
You can't go to any other.
Yes,
Okay.
exactly. Exactly. In other words, suppose I had this. Natural log of -x plus natural log of -x equals 1 or 0, let's say. Okay? Well, if I combine these, I get the natural log of x squared. I'm not going to violate any domains if I use this. No matter what x is, I'm not going to violate any domains. But in this line here, x has to be negative. If x isn't negative, I'm violating both of these domains. Once you've compressed it, it becomes x squared, and no matter if x is negative or positive, this would be positive. So you got to be a little careful with these compression rules. It seems odd that they tell us a rule for logarithms, and yet it's not exactly ironclad rule. It certainly is not a rule for checking domains.
All right. Well, I guess the next problem.
Yeah.
Let's see. So I'm just trying to find one. Figure out. I guess let's look at this one. 1 minus 2 natural log x equals -4.
Okay. First step and second step.
Let's subtract 1.
Okay. And then divide by -2.
Mm-hmm.
So what's the answer for x? How do I solve for x? Now I get it to this point.
Wouldn't it be x equals e to the 5 over 2?
Yes. Exactly. X equal e to the 5/2, which, of course, you can get that out of your calculator. In fact, that's about the only way we're going to get that. I don't know how to take a number like e and raise it to the 5/2 power. I guess you could take the square root of it and then take it to the 5th power. Now, we're only doing a half hour tonight, Garrett, is that right?
Yeah.
Okay. We certainly have time for another problem or two.
I guess we should. 2, or I think, no, we haven't done this one. 2 sorry. 2 natural log of -x plus 7 equals 14.
The plus 7 outside the paren or inside?
Outside the parentheses, yeah.
Okay. Equals 14?
Mm-hmm.
Okay. So I've got the natural log of -x equals 7/2.
Mm-hmm.
Okay. So what now?
The only thing that is kind of thinking out about this is, even if it has parentheses around it, it would still be the same as multiplying, right? So
Exactly. Well,
okay.
yeah, in other words, you can treat the argument as -x. So use the same rule. E to the 7/2 equals -x.
Okay. Sorry, it's just that threw me off when I saw it. I don't know why.
Which means x is equal to minus e to the 7/2. And that, of course, is going to be a negative number, because the minus sign is not acted upon by the 7/2, so you take e to the 7/2, and then it's minus whatever that number is. But notice that's what we need x to be, is negative.
Yeah.
If x were positive, we would be violating domain. But as long as x is negative, then you're going to have a negative times a negative, so you'll have a positive number inside the argument.
So it wouldn't be extreme. I guess maybe let's get one last one. 10 natural log 100x minus 3 equals 117.
Did I write that right?
Mm-hmm.
Okay. So natural log of 100x is equal to what?
120.
Divided by 10.
Oh, divided by 10.
It's okay, I did 2 steps in one. And so now we have e to the what? I always start with the left side just because I'm so used to saying it's the number on the far left raised to the number on the far right equals the argument. So I noticed when you gave it to me before, you started with the argument. That's fine. There's nothing wrong with that. So that's equal to e to the 12th power. So x is equal to e to the 12th power divided by 100. So these are all pretty much the same, these 4 or 5 problems we just did.
Yes.
Isolate the natural log, and then switch it to exponential expression, and then solve it algebraically.
Yeah.
Notice that exponential expressions are not algebraic expressions. They typically can't be solved algebraically. I mean, they can as long as the variable is not in the exponent. But typically, if I tell you that 3 to the x equals 10, you have no way to solve that algebraically.
Yeah.
So that's why we came up with logarithms. Or that's why mathematicians came up with logarithms. Is because I can express that logarithmically. I can say the log base 3 of 10 equals x, and now I can get that number out of my calculator, because my calculator has massive tables of log tables. And in fact, when I went to high school, we didn't have calculators with log tables in them. And at the back of every math book were these huge tables for logs, natural logs, and trig functions, because you didn't have any other way to get it. In other words, if you asked me what the natural log of 7 was, when I was in high school, I had to look it up in a book. There was a table in a book that, had columns and rows, and you looked up natural log of 7. At least now you can do all that on a calculator. But there's no algebraic way to do it. That is not an algebraic expression. It can't be solved algebraically.
Yeah.
Okay. Any other questions, Garrett?
Other than that, I wouldn't have any other questions, really.
Okay. Okay. Well, I will sign off and talk to you next time.
All right, sweet. Thank you.
All right. You're welcome. Bye-bye.